I would like to start by thanking the organizers for this very nice meeting. I've enjoyed it a lot, and I think it's been very productive. Also last week, I was here with one meeting a course. It was very nice. And so I'm going to talk about screening mechanisms, and of course I have a few spoilers by David. I'm also Nelson. I don't know if you have some spoilers. I should try to do my best. And what I would like to tell you about is that David was explaining when we want to explain the cosmic acceleration by referring to some light scalar degree of freedom cosmic scale, we track this the cosmic expansion. Then we will have effects on small scales that somehow we want to hide. And sometimes maybe we rely too much on these screening mechanisms, and we get this very nice model that gives us acceleration. And then we rely on these screening mechanisms to avoid local gravity tests. And then I will try to argue that one should be careful when doing this. So I start by showing how you have these forces. Yes, I can go very quickly through this because I explained that already. And then it's for screening. Then I will explain the chameleon and the symmetron and the Vainshtein mechanisms in a bit more detail because I want to point out where the difficulties are when you want to explain both cosmic acceleration and local gravity tests. And then I will try to explain what screening really means, because it means something and not something else. And that's what I try to explain. And then how, when we understand what screening really means, we can see that you can pierce this screens that you have and have effects from the cosmological evolution of the scalar field in local gravity observables like lunar range and anomalous propagation field of gravitational waves that then you can constrain with binary pulsars. So I will start by defining what I will mean by dark energy and self-acceleration. Because what I will be talking about is the difficulties to have self-acceleration while being compatible with local gravity tests. So usually when you have your modified gravity or your dark energy model, at the end of the day you get this modified Freeman equation, where you have the usual Freeman factor here, and then either you modify the energy budget of the universe and you introduce some fluid or some effective fluid with negative pressure, and then that will give you the acceleration, and this is what I will call dark energy. But you can also have acceleration, and this is what I will call self-acceleration, by modifying the effective coupling of this effective Newton constant. To give you a more explicit example, let's take this f of r theory, and we know that we can go to the Einstein frame, where the effect of the modified gravity is encoded into the presence of this additional scalar degree of freedom. So gravity is described by the usual Einstein-Hilbert action. You have this canonical, or this scalar field with a given potential, but now this scalar will couple to matter to this effective measure. Okay, so then you can get acceleration from two different ways. One is if this conformal factor is essentially 1, you can have a very flat potential, and then you have acceleration, inflation, or the usual one effective cosmological constant. The other possibility is that this conformal factor is actually relevant, it's not close to 1, and you can get effective acceleration from this coupling to 5. Okay? And this is what I would call self-acceleration. Okay, so, and then, as we can see, we're seeing this scalar field couples to matter usually through the trace of the momentum tensor, and this will give you an effective potential that is the usual Newtonian potential, this Gm over R, But then the effect of the scalar field will give you this Yukawa potential in addition to the usual one that will have some coupling constant and some mass. So then you could say that for dark energy you usually need a very light scalar field, and that means that the mass should be very small, and then the effect of this Yukawa suppression will only kick in on very large scales, essentially super Hubble scales. So this effect is just 1 plus beta, then maybe you could reabsorb into G, okay? And then you can say that you are actually measuring G times 1 plus beta. The problem with this is that if you put an object here, you have this interaction, you have a change of gravitons on the scalar field, and then you can say that your G Newton is describing the effect of both fields. But now if you look at the ray of light, this will only see the gravitons, so this G as observed by the bending of light and by this free-falling experiment will be different. Okay? And this is where the problem comes in. Because what I'm saying is that this scalar field will give you an integral contribution to the slip parameter to gamma PPA. And then the way to avoid this problem is by introducing some screening mechanisms that can be, well, this is a nice way of summarizing all of them. I think that we also show this action. So usually you have this non-trivial kinetic term, where it will depend on the background value of the field, this effective mass, and the coupling constant. And then you have all these kind of screening mechanisms. In the symmetron or gigaton, you play with the coupling constant. In the chameleon, you play with the mass. And in Vainshtein, kinetic or camouflage, you play with the kinetic term. And you make it environmental dependent, so you can hide scalar field in dense environments. Notice that there is an obvious screening, and that is making this 0 everywhere. Okay, but this is the usual quintessence. It's not very interesting phenomenologically, so I will not consider that. So let's look at the chameleon. As David also explained, you have this effective potential. So if you are on cosmological scale, you have the cosmological density. You have this usual potential, bare potential. You have this conformal factor. And then the effective potential will be this one, the field will sit here. Now you go to galaxy scale, the energy density increases, so the field gets fatter and then moves towards a smaller value of the field. And then this is what gives you the mass on the, let's take the laboratory density, and you get 40 microns, so it's okay. We don't offset this, it's fine. The problem is that if you take solar system scales, you get 10 to 6 astronomical units. And that means that we should observe this, this interaction in the solar system. The way to avoid to solve this is that there is an additional effect that I think David didn't mention. So this is new. And it's this thin shell factor. So if you solve the equation for the scalar field, for the scalar field profile, when you have a compact object of radius 1 here, with an density inside and a different density outside, so you solve the equation, and here you get the Yukawa suppression, this is the coupling, and you get this additional thin shell factor. And this essentially measures the variation of the field from outside to inside. So if this is sufficiently small, this will give you an additional suppression. And this is how you actually suppress the field source. Okay, and this is something we've been discussing too, and is that this screening mechanism depends on the environment. So if you have an object here, it will depend on whether you put it here or somewhere else. It will be screened. Okay, and this is because this thin shell factor depends on the phi. This is the surface gravitational potential of the object, and also depends on the value of the field outside. Okay, so it will depend on whether it's in a void, if you want, or inside the cluster. For this model, there is a novel result. It was in this paper very nicely. And the thing is that if you take the cosmological scales, and at this case you have this variation of the effective potential, and then to avoid local gravity constraints, typically you need that the variation of the conformal factor from the Milky Way to the cosmological scale must be smaller than 10 to the minus 6. This is because these are the constraints we have from gamma PPA. But now, if you go to redshift 1, the density, the cosmological density at redshift 1 is between the galactic density and the density at redshift 0. And that means that the variation of this conformal factor from redshift 1 to redshift today must be smaller, or it's smaller, than the variation from the Milky Way to cosmological scales today. And that means that if we have this constraint, it means that because the conformal factor cannot change more than 10 to minus 8 from ratio 1 to ratio 0. And this is what prevents of having self-acceleration. This means that the conformal factor cannot have any cosmological effect. You will want to avoid local gravity constraints. It's even worse, and this is why David was looking at this case, and is that if you compute the typical mass of this field and use this constraint, you get that this mass must be smaller than this value. This means that you can only have effects if you want to avoid local gravity constraints. You can only have effects on scales below megaparsec. And that's why going to nonlinear scales and making embodied simulation for these fields is so important, because this is the only place where you expect to find the effects. For the symmetron, we have again this potential that it explained, and well, it's the same. You have similar problems. You also have this no-go result that you can only have effects on below megaparsec scales, and you have this paper by David and Claudio where they simulated this, and it's very nice because here you can see the formation of these domain walls. So these colors, yellow, orange, and green, correspond to the field going to one of these two minima. And then you see that in the evolution, this will tend to collapse. And when it collapses, it emits some waves here, these scalar waves. Okay? And this is what Robert was explaining on Tuesday, that these scalar waves can penetrate the galaxy or our local gravity environment and give you a non-trivial correction to the gamma ppm. See this talk. And we developed this similar mechanism for a vector field. It's a symmetron kind of. It's very similar. The only difference is that here you cannot play with an effective potential because you have these different components. But you can look at the critical points. You have this Lorentz invariant vacuum. You have this Lorentz vibrating vacuum, and you can choose the parameters so that the vector field at the minimum is space-like, because this is what we want. And then we can neglect the temporal component. We can rewrite the equations by neglecting the temporal component. And then now we can write an effective potential for this spatial component, and then play the same game as with the symmetron. Okay? So we have this effective potential, and then when the density is very high, when it's very low, the field will sit here at the minimum. You have a Lorentz invariant vacuum, but below a given, above a given value, the field will go to this minimum. You will break spatial rotations, isotropy. So this is a signature of this model with respect to the symmetron, because in the symmetron you have a phase force, and that's it. Here you have a phase force that will be direction dependent, because you are breaking isotropy. And you can see the profile, and this is the force, where you can see here how it depends on the direction of the pattern value. You have this also this. I will skip this, but you have this additional term with respect to the symmetry. But this is what I would like to point out, that in this model you also have violation of Lorentz. And now with the David and Claudio, we are trying to implement this into an embodied simulation, and we expect this direction-dependent force to give you a modification in the shape of voids, for instance. That will be a signature of this kind of spinning mechanism. For the Vainshtein that was first discovered in massive gravity, I'm going to take the simplest example where you can find it. Probably this is a cubic Galilean toroidal around a spherical symmetric object. You can write the equations like this, and then it's very easy to see why this screens the phase force. If you are on very large scale where this term is negligible, you get the usual force phi prime 1 over r squared. Okay? This is the gravitational force, and this is the force mediated by this field phi. But then at some point this term will start dominating, will become the same over this, and then it will dominate, and then you will see that the force goes like 1 over r, 1 over square root. Okay? So you see that it's suppressed with respect to the gravitational force. And this is important. Like in the chameleon in the symmetron, the screen of an object depends on whether you put it here in a void or in a cluster, because it depends on the environment. In this case, the only parameter that will fix the spinning of the object is the mass. Okay, so you give me the mass of an object, you can compute this Vainshtein radius, the scalar this terms are dominating, and that's it. The only thing you have to make sure is that the object is smaller than its Vainshtein radius. Okay, but it doesn't depend on whether you put it here, or in a void, or wherever you want. And it's very, I think, I wouldn't say demotivating, but because if you compute the Vainshtein radius of the sun, it's on the size of the whole galaxy. Now, if you compute the Vainshtein radius of a galaxy or cluster, this is close to the Hubble horizon. So that means that in our universe, for realistic models, pretty much everything is screened. So you don't expect to see any effects from the sky, or at least it's very difficult because it's very efficient. Also, these screenings have theoretical problem that has to do with superluminarities, because in these solutions, when you compute perturbations, you typically find a direction along which these perturbations are superluminant. I think it's not very clear whether this poses a problem for a UV completion of these theories or not. This is under investigation, I would say. Another more exceptional problem is that you see that here you get two branches, because this is a quadratic equation for 5 prime. If you include higher terms, like Galileo 4, Galileo 5, you will get a fifth, or I think it's a fifth equation. So you have many branches. And when you want to match this screen branch with cosmological branch going to the void, in the void usually this solution becomes doesn't exist, because it becomes imaginary essentially. And that means that if you are in a cosmological evolution and you start getting voids, inside the void you might have instabilities or a breakdown of of the theory. Okay. Yeah, that's important. So now I'm going to explain what screening really means. So I will try to explain to give you an idea of what I understand by screening. And for that, I'm going to use the framework of Vainshtein theories that was described by Vainshtein. It was obtained by Vainshtein in '74, and then we discovered later, recently. And this is the most general scalar tensor theory with second-order process of motion. I think most of you are familiar with these theories, and it comprises many different non-theories like intentions, but tuning, or this. It's interesting that they are somehow they are invariant under the formal transformations. Juan and Miguel. They show that if you consider only they call special decimal transformations, where the conformal factor only depends on the field, but not on the kinetic term, then this class of theories is invariant under this transformation. If you include an X dependence in the conformal factor, then you go out of these theories, but nevertheless they will be safe because they are connected to this up to a field definition. And also by studying the AFT of dark energy, some people, Rices and Nietzsche. They obtain a larger class of theories beyond this one, where even though you have third-order process of motion, you have a set of hidden constraints that reduce the number of degrees of freedom to the correct one. And here I also like to show this, because this paper was published in '74, and you see that it was completely ignored, neglected for 30-40 years until they got this paper, where then started receiving some attention, let's say. And I think some of you already know this story from Vainshtein, that he quit physics. He was a student of Beltran, he quit physics, he became an artist, like now. And then recently, he became aware that he was becoming very famous in cosmology, and then he started publishing again. That year, he came up with this a simple theory of quantum gravity, which is, I guess he was waiting for the world to be ready for this. And then, earlier this year, he started working on these scalar tensor theories, with third-order scalar tensor theories, this beyond Vainshtein. And then in the acknowledgements, it's very nice that he was, because he got an email from Villera, and he said, this thesis provided me with an introduction to the efforts of those people who were trying to find third-order scalar tensor field theory, the so-called beyond Vainshtein theory as well. So long as I'm alive, no one goes beyond that. So now let me take this general framework, and then let me consider a solution where I have the background scalar field, background value for the scalar field, and I'm going to expand around it. Okay? I'm going to linearize in gravity because we know that even if you have high density, the gravitational potential is always small. Maybe it's a near black hole or neutron star, but everywhere in the universe, the gravitational potential is small. So I'm going to linearize in gravity. But for the scalar field, I'm going to keep all the non-linear terms. Okay? And then you have the coupling of gravity to matter and the coupling of the scalar field to the phase of the element to pressure. Yeah, I'm cheating a bit because but my fault. So then when you say that you are screening this field phi, what you are doing is that you are relying on these nonlinear interactions, either from the potential or from the derivative set interactions, to screen these forms. Okay? So to screen the interaction of phi with matter fields. But you see that the background value will also enter here in the propagator of the graviton. Okay? And this you will not screen. So then you can have non-trivial effects from here. From the propagating gravitons, from gravitational waves, you will modify the propagator. Typically, if you are in cosmology, this will give you an anomalous propagation speed for gravitational waves, okay, coming from the cosmological evolution of the scalar field. And you can also modify the effective coupling of gravitational waves to its source, to the anisotropic stress. Okay? And notice that this is different from the one you have in Poisson equation. And then, for the potential gravitons, for phi inside the Newtonian potential, you can modify the effective Newton's constant in the Poisson equation, and you can also have you can also modify the PPM parameter, the split parameter. Okay, and now you could say that I was saying that you screen the effect in the Poisson equation, but remember, when you write the effective potential, you have G m over r 1 plus beta exponential of rho. Okay, when you suppress the field, when you screen it, you screen the beta term, but you can have an effect in G, okay, in the variation of G Newton. And then this is important for shift symmetric theories. Okay, so if you don't have shift symmetry, by shift symmetry I mean that you can add an arbitrary constant to your field, and then it's the symmetry of your theory. If you don't have that, as is typical from CHAMELEON and symmetron, then inside the dense environment, you will develop given effective potential, and then the field will sit at the minimum of this potential. Okay? And this is the way you will effectively decouple the local value of the field from the cosmological evolution. Okay? So then you cannot penetrate this green region. However, if you have shift symmetry, you will not have any potential because of the shift symmetry. For this, the potential, having potential, and then the local distribution of matter will not determine the local value of the field. It will only determine the spatial gradients of this field. Okay, but the temporal gradient will still be given by the cosmological evolution. Okay, so in this case, the cosmological evolution will penetrate the screen region, and you can have an effect in local gravity observables. Okay. In another way, if you want, all these theories, they have an approximate Galilean symmetry, where you can add an arbitrary gradient to the field, and this will be a solution. Okay. So if you take your solution in the solar system, so in this inside the screen environment, this will give you. You can always add the cosmological gradient, and this will be a solution. So the local solution will be a linear superposition of the radial gradient given by the local distribution plus the cosmological gradient. Okay. So, but then we have very tight constraints from G Newton, for instance, and that's what they explore in this paper. From the lunar laser ranging experiment, you have that the variation, the time variation of G Newton is to the order of 10 to minus 2 extra. Okay. And then in this series, the variation of G Newton is given by the variation of the conformal factor. That can be written in this form. So this is variation with respect to phi and then phi dot. As I said, phi dot is given by the cosmological evolution. And then, whether you are in matter domination or in scalar field domination, you have that phi dot is given either by alpha h or h. And that means that this will constrain order 1 couplings to matter from the component factor. So this alpha must be smaller than 10 to minus 2, 10 to minus 4, something like that. And again, this tells you that you cannot have cosmological effect of strong gravitational effect from the conformal factor. Okay. This doesn't mean that you cannot have that any from here. It's got thing that we were discussing. That's why you always need to add a cosmological constant to your potential to have dark energy. Okay. The other possibility, or the other way where you can constrain the series, is by looking at the anomalous propagation speed of gravitational waves. Okay. As I said, the Lagrangian for the gravitational waves will have an anomalous propagation speed and some coupling, effective coupling, gravitational waves. That will be different from the one here. So this is different from G Newton. Then you can use this little trick here to write this like the usual gravitational waves with C equal 1, and then you can compute very easily the emission, the energy loss by binary pulsar of by any system. That is simply given by this expression where CT appears here. And then, in the same trick, you can compute the solution for the polar solution. And the only effect is that G is replaced by G gravitational wave, and here you get 1 over CT. And now you can combine this and compute the analogous of the pole formula, where the only difference is that here you get G gravitational wave, and here you get CT. And now you can use this to compute the variation of the period of a binary system by the emission of gravitational waves. And then all this part here is the same as the R, and the only modification is this factor in front. Okay? You see that if G gravitational wave is equal to G Newton and CT is equal to 1, you get the GR result. Okay? But otherwise you have this factor. And here, let me tell you that, of course, if you have a binary pulsar, if you have this scalar field around coupled to matter, this will also emit scalar waves. But then this is where the screening is efficient, because either you have a high mass or this small, or what, sometimes using shift symmetry theories, this will become very large, and that means that you have a screening of the emission of scalar waves. So it will be not very efficient. But then you can go to the full-scale binary pulsar, use this formula, and compute the constraints from the observation. So you can compute the masses and all that. And at the end of the day, you get this constraint that is at the level of 10 to minus 2, 10 to minus 3 on this factor. Okay. So now, if G gravitational wave is similar to G Newton, then you see that this gives you a very tight constraint on CT. Okay. And this effectively this gives travel to Kondensky 4 and 5, because those are the only terms where you will find variations of the propagation speed of gravitational waves. Okay. Now, from gravitational wave astronomy, you could expect to put even tighter constraints on this CT. With the observations of LIGO, you cannot do that because in the first one, the post-Newtonian phase is very short. Here is longer, so you would expect to have tighter corrections, but the sensitivity is not enough to improve our constraint. Okay, so our constraint from the binary pulsar is still stronger than the one you would obtain from here. A very nice possibility discussed in this paper is that when you have all the interferometers, then you can look at some binary system, and then you can map the electromagnetic signal, so you can measure the period of the system. The period of the system will give you the frequency of the gravitational wave emission. It's twice that. So then you can monitor both signals, and by comparing them, you will see if C of photons is the same as C of gravitational waves, or they are different. Okay. I think that's interesting. And then what the conclusions I would say is that we have all these scalar fields in high energy physics, modified gravity, in Kondensky, and so on. We have scalar fields from everywhere, and we rely on screening mechanisms to have cosmological effects while being compatible with local gravity tests. But then I think that this, well, I hope I convince you, I think it's very convincing that you cannot have self-acceleration from these scalar fields while being compatible with local gravity tests. So at the end of the day, even if you have this scalar field, the acceleration must come from an effective cosmological constant because of this normal result. And then for these shape symmetric theories, you have that the cosmological evolution can actually penetrate the screen regions, and then you will have variations of G Newton and anomalous propagation speed of gravitational waves that then will tightly constrain quantity and quantity of the theory. So actually, it's much more general than this. It's for any theory that gives you an anomalous propagation speed of gravitational waves. So this only also applies for beyond Vainshtein or vector tensor theories or any theory that gives you CP different from 1 at the order of 10 to the minus 2. And with this,
one or two quick questions.
So the constraint you show for the lunar is arranged in binary groups. Are they for models with shift symmetry or in general?
yeah,
just
shift symmetry.
Just with shift.
Because those are the only theories where you cannot decouple the local value from the cosmological evolution.
Okay. Best thing for